Thank you very much. And I would like to thank the organizers for the conference and for the invitation to speak here. So I will be talking about CFTs with conformal field theories with UM times UN symmetry. And I will present results of some conformal bootstrap analysis I have been working on for a little while now with Stefanos Kouzvos. This is going to be a paper on this, hopefully this month. So let's start with, you heard something about the bootstrap already, but perhaps we should start with a little bit of the logic behind it. And the logic is different compared to renormalization group methods that you may be more familiar with, which rely on thinking about the renormalization group flows and their endpoints. So we always imagine that we are in some UV conformal field theory, maybe often a free theory, that we then deform with a relevant operator, which results in a normalization group flow, and then it terminates in the other endpoint in the infrared into some other conformal field theory that perhaps is strongly coupled or non-trivial more generally that we want to understand the properties of. That flow is governed by the beta function, and zeros of that beta function are the fixed points of the normalization group. Now, the conformal bootstrap takes a completely different approach. It wants to completely get rid of this thinking and focus completely on the physics at the fixed points only. There will be no mention of how we got to the fixed points, what relevant operator would be formed by some UV theory to get to this IR theory. None of that information can be captured by the bootstrap. But regarding the conformal field theory that we are assuming we are probing, we will be able to understand a lot of aspects of it, including its spectrum of operators, scaling dimensions, OPE coefficients. That will give us basically a very good picture of the conformal field theory data that we're interested in and that are of relevance to experiments as well as theoretical, for theoretical questions. The way the conformal bootstrap does this is by considering constraints on 4-point functions of operators in the conformal field theory. Now, when we have conformal symmetry, 2- and 3-point functions of operators are fixed up to constants. There is no, the kinematics is completely fixed. The things that, the quantities that appear are the OPE coefficients or Wilson coefficients and the scaling dimensions. But the X dependence, if you want, of the 2- and 3-point function is completely fixed. In the 4-point function, this is not true because if you have 4 points in space, you can construct 2 separate conformal invariants. So the 4-point function will have some overall fixed X dependence, but then an arbitrary function of those conformal invariants can also appear. And looking at the 4-point function in the OPE decomposition way, where you bring operators together, you imagine they exchange an operator, and then that operator is also exchanged by the other 2. You can write a schematic representation of the 4-point function as you see here. And there are 2 different, well, there's more than 2, but it turns out that 2 of them give non-trivial, that one of them gives non-trivial constraints here. These ways to bring the operators together give rise to the crossing symmetry equation. Here you see that on the left-hand side, I bring together O1 and O2, and on the right-hand side, I bring together O1 and O4. And since it's the same 4-point function that we are discussing, it better be that these 2 different decompositions of the same 4-point function have to be the same. Now, if on top of this, you assume unitarity, which basically says in this context that operator dimensions lie above a certain unitarity bound, and the OPE coefficients denoted by C here, for example, C120 on the left-hand side, are real. So crossing symmetry plus unitarity turns out to lead to highly non-trivial constraints, as was realized a few years ago, maybe 12 or so years ago, numerically, because the resulting equations are very complicated and not easy to deal with analytically. However, numerically, we saw that they give rise to highly non-trivial constraints on the spectrum of theories. So the way we solve these bootstrap problems, and I should I should perhaps mention here that we call this the bootstrap because, you see, we're not solving any dynamics, we're not evolving any theory and trying to follow that evolution dynamically. What we're doing is we're using just constraints that the theory has to satisfy, and those are so restrictive that they allow us to uniquely determine, in some cases, theories that can satisfy them. And so it's this logic of getting something out of nothing in some sense. So more recently, this has been developed numerically because it was realized that we can map it into a semi-definite programming problem, and there are many algorithms and highly developed algorithms to solve such problems because they appear all over the place in science, also in industry. And the primary reason for the excitement behind the conformal bootstrap is, of course, that the results one gets are non-perturbative. There are no approximations involved, and therefore it is one of the few methods, along with, of course, Monte Carlo, that we have to probe the non-perturbative regime of conformal field theories. Now, the most striking results of the method so far have been found for three-dimensional conformal field theories, and those are very important due to their applications to classical critical phenomena. In particular, the Ising model has been analyzed to really great detail, as have the ON models. In my work, I have also analyzed other universality classes like the cubic universality class you may have heard of, and others. There has also been a lot of lattice work in some of these. The bootstrap has also been applied to superconformal field theories, defect CFTs. This logic of the bootstrap has been adapted to treat all these types of problems. And today, I want to discuss the application of the conformal bootstrap to the chiral phase transition of QCD. Perhaps I hope that this will be of interest to the audience, given the interest, of course, in QCD and its properties. So let me pause and ask for any questions up to this point.
I don't see any questions.
Okay, very
Please
good.
go ahead.
Thank you. So let me just summarize a few known things to everyone there, I'm sure, about the chiral symmetry of QCD. So if we start with the Lagrangian of QCD, and we will imagine we have NF general, NF fundamental quarks. At the classical level, we have UNF left times UNF right global symmetry, which we will write as SUNF left times SUNF right times some vector and some axial part. And the vector part, the U1B part, is not chiral, so we will forget about it. And there is also a very concrete understanding that at zero temperature, the U1 axial anomaly symmetry is anomalous and therefore broken. And so we end up in the quantum theory with SUNF left times SUNF right global chiral symmetry. Now, in the vacuum of QCD, the quark condensate, which is Q bar left, Q right, breaks the chiral symmetry, and the pattern of the symmetry breaking is such that SUNF left times SUNF right goes to the diagonal SUNF. And this is the situation. This breaking happens at some non-zero temperature, where for the case, for example, of two massless quarks, as we will review later, it's about 160 MeV. Now, there are two quarks that are much lighter than these, up and down, and a third one that's a bit lighter, the strange quark. And therefore, when we study the nature of the order of the chiral phase transition of QCD, we are considering either 2 or 3 quarks as massless, and the rest are considered infinitely heavy, compared basically to the critical temperature that we have. So in this context, we want to understand what the order of the chiral phase transition is. It's a phase transition that happens at some non-zero temperature, and it is not clear what its order is. Is it first order or is it second order? And this was a question first posed by Pisarski and Wilczek in 1984. Now, The breaking of the axial symmetry of the axial U1 in QCD was, of course, understood by 't Hooft to be due to instanton effects. This is very well understood at zero temperature. But in various papers and old work by Pisarski and other co-authors and authors, the non-zero fate of the U1 axial symmetry has been the subject of sort of controversy, as far as I understand. I'm not an expert in this, and there are people in the audience that know much more about this than I do. But it is my understanding that although at zero temperature, of course, the effects of the breaking are there and the axial symmetry is broken, at non-zero temperature, there is a suppression of the instantons. It's an exponential suppression where rho here is the size of the instanton. And this exponential suppression that may suppress the effects of the axial anomaly breaking and therefore result to the axial symmetry being effectively restored at high temperature. This has been studied theoretically. There have also been lattice simulations that have tried to see if the breaking of chiral symmetry of the axial part of the chiral symmetry persists at non-zero temperature. And the conclusion to me, by looking at the literature, seems to be that at high enough temperature, indeed, and close to the critical temperature, indeed, the axial symmetry is restored. So this is the question is if SUNF left times SUNF right times UN axial at non-zero temperature should be reduced to SUNF left times SUNF right. In the high temperature phase, what is the global symmetry? Because we need to know the global symmetry at the high temperature phase in order to find potential universality classes of theories that a potential second order phase transition for QCD might actually be part of. And for example, if you have two massless flavors, you either have O4, which is SU2 times SU2, or you have O4 times O2. And of course, we all know the O4 universality class. So if the axial symmetry is not effectively restored at non-zero temperature, there is a belief that the symmetry, the chiral symmetry breaking is of second order and of the O4 universality class. But if it is effectively restored, then we have O4 times O2, and it is of interest to look for universality classes with that global symmetry to see if in that case, the chiral symmetry breaking of QCD may be second order. So this brings us to the study of the so-called times UN models. Of course, we're looking for a theory in 3 dimensions. We're looking for a conformal field theory in 3 dimensions. And in order to model this, we will consider the field phi, which you can think of as the quark bilinear that I mentioned before. This is the order parameter of the symmetry breaking. It has 2 indices, A and R here. A runs from 1 through M for the and R runs from 1 through N for the UN, and it's a bifundamental under times UN. If you were to write down a Landau-Ginzburg theory for this matrix, you would write this Lagrangian over here. You have 2, you would write, of course, your free theory. You can add your mass term, and you would have 2 couplings. One is the square of the trace of phi dagger phi, and the other one is the trace of the square of phi dagger phi. And when you compute the beta functions for these couplings lambda and g in 4 minus epsilon dimensions, what you find is that there are up to 4 fixed points. The Gaussian fixed point is always there, where lambda and g are 0. You have a fixed point with enhanced symmetry. If we set lambda to 0 and keep g non-zero, then the symmetry enhances to O2 times m times n. And then there are 2 fixed points where lambda and g are both non-zero, but typically are denoted by this U plus minus in the literature. Now, these fixed points don't exist for all values of m and n. If you take some m and sufficiently high n, then you are in this situation 1 here, where you have the fixed point U plus being the renormalization group stable fixed point. You have the Heisenberg fixed point, or not Heisenberg, but I mean the O2mn fixed point also there when g is 0. And you have the U minus fixed point and the Gaussian fixed point, and U plus fixed point is stable. But as you change n at that for fixed m, the two fixed points U plus and U minus move around in this plane and they actually collide. When they collide, we lose them as unitary fixed points and we transition into situation 2, where we only have Gaussian and Heisenberg and none of the two are stable. As you keep changing n, the two fixed points actually reappear in the real plane, but now they appear with the opposite coupling G, the opposite value, the opposite sign for the coupling G. And U plus remains stable. And as you keep changing things, so that's situation 3, and as you keep changing things, then the coupling of U plus, the G coupling of U plus changes sign again, so that it's the orthogonal fixed point, the one denoted by H in situation 4, that becomes stable. Now, the values where these transitions happen can be computed in the epsilon expansion, and there have been many papers recently, over the years, and also recently doing this. One thing to point out is that for the correct symmetry break-in, where we want SUNF times SUNF to go to the diagonal SUNF, we need this coupling G to be positive in order for the potential to break the symmetry in that specified way. And of course, we also need a fixed point to be RG stable, because we want our RG flow to reach that point. We do not want a relevant operator beyond the mass operator at that fixed point. So the question is then, if we go back one slide, what are the values of M and N for UM times UN fixed points for which we are in situation 1, where we have G positive and the U plus fixed point being stable? This is what we want to look for. And in the epsilon expansion, what's typically computed is the quantity n plus of m in 4 minus epsilon. So we fix m and we compute the value of n for which we transition from situation 1 to situation 2. And we want to be at an n higher than the critical n we computed, so that we are in situation 1. There have been many papers computing this over the years, as I said, and this was recently done up to 6 loops, which is order epsilon to the 5 for this quantity. And of course, we need to take the epsilon to 1 limit, but and this is something not well defined, but let me show you how these expressions look. So if you fix m to 2 and you compute this n plus in 4 minus epsilon, you get this series over here. It's not going to be a convergent series or anything. We know it's asymptotic, but there have been various resummation techniques employed, and for m equal 2, the result is that the critical value of n is about 4.4. So you need to have, in a UM times UN theory with m equal 2, you need to have an n of 5 or higher in order to be in situation 1 and have a stable fixed point that can host a phase transition that is second order. This is clearly not the case for QCD with 2 massless flavors, because that would then mean that the 2,2, the theory with m equal 2 and n equal 2, which is the case of QCD with 2 massless flavor, falls below this value. N is 2 and therefore below this value of 4, and the theory does not have a fixed point. Therefore, the phase transition in that case would have to be first order. You can repeat the same exercise for m equal 3, and then again, you see that the n that you get is larger than 3, and therefore, again, in this case of 3 massless flavors in QCD, you do not have the possibility of a second order phase transition. Now, this relies on resummations after the epsilon expansion. There has been some work where people resum the beta functions themselves and then look for fixed points of the resummed beta functions. And those are not guaranteed to be the same as the ones that you find in the unresummed beta functions. There have been some hints doing that there is a distinct universality class than the one discussed in the standard epsilon expansion, but the fact that these are uncontrolled approximations perhaps is unsatisfactory, and we would like to have a better way. And the better way that we are going to pursue here is the conformal bootstrap way. And This relies looking on a 4-point function. So here we will look at the 4-point function of the order parameter operator. We have phi, phi dagger, phi, phi dagger, and we will analyze this in all possible channels that it has. And first, we need to understand some of the group theory. If we had phi in the fundamental of UN, just one UN, then we know that if we bring phi and phi dagger together, what it exchanges is singlets and adjoints. And if we bring phi and phi together, it just exchanges symmetrics and antisymmetrics. These are representations of every spin, but under the global symmetry, they fall into these irreducible representations. Since we have UM times UN, and products of irreducible representations are irreducible, what we need to consider are products of these representations of UN. So the group theory here is actually not hard at all. It is easy because we know so well the group theory of UN. And here are some results. Let me show you some bootstrap bounds. So what we do with the bootstrap is we make an assumption on, say, the value of this operator phi that I was discussing here. We're in 3 dimensions, and therefore the lowest dimension that operator phi can have is 1/2. And then we are asking for what is the highest possible dimension of one of these exchanged operators. So we consider the OPE of phi with phi. We look at all the different irreducible representations on the other side, and we choose, for example, the spin 0 operator in the representation RS that I plot here, where RS means that I take the adjoint from the UM and the singlet of the UN. There's going to be such an irreducible representation on the right-hand side, and I want to find the maximum dimension for the operator of spin 0, the leading operator of spin 0 in that representation, for a given value of delta phi. And these are the kinds of plots you get. And you see very sharp kinks for large n, for example, the 220 theory here. And you can perform analytic computations at large n. We also did this it hadn't been done before, but we did it in this paper that will be coming out. And the dot that you see, the circle and the square that you see there are exactly the the U plus and U minus fixed point. The square is the U minus fixed point, the U plus fixed point is the circle. And at large n, you see just how well the kink in the bootstrap bound coincides with the position of the fixed points as derived from the large n results. When we look at n equal 10, it's still very good. Of course, as we decrease n, this becomes worse. And you see that the kink becomes milder and eventually disappears once you get to the to low n. This behavior of the kink, we believe, is basically the result of the fixed point moving into the non-unitary regime as we decrease the value of n. But it is very important that both universality classes are allowed here. You see that one saturates the bound, the other one is in the allowed region. Everything below these curves is allowed in the corresponding theories, everything above them is excluded. And this is a fully non-perturbative result. You can also do something else. You can take the singlet from U2 in this case, and the adjoint from UN, and get a bound on the corresponding leading spin 0 operator. And these bounds don't have spectacular kinks, but I'm just showing them to you to show you that indeed, again, they seem to be saturated at large n by, in this case, the other fixed point, the U minus fixed point. So here, it was the circle, the U plus fixed point, that was saturating the bounds. And here it is the U minus fixed point, which is the square that's saturating the bounds. So it's a good check, of course, on our computations at large n that we have set up the problem correctly, that we are doing the numerics correctly, that we are not excluding known theories, and this lends validity to our computations. Okay, so let's focus now on the U2 times U2 theory. The U2 times U2 theory, you can get bounds on all sorts of different operators. And these are all bounds on spin 0, leading spin 0 operators in the different irreducible representations of the global symmetry. You can think of them as quadratic operators. You take one phi and another phi, they have indices, and you bring these together in different ways to have the different irreducible representations, but they are all quadratic in phi. and no derivatives. They are spin zero, leading operators of spin zero. So you get bounds for all of them. And what I have denoted by the blue dot here is the O8 model, which is, of course, in the allowed region of all these curves. And while there are no kinks here, you see a kink in the AA bound. So here I have a plot just for that. So you take the antisymmetric from each of the U2s.
And do you have 5 minutes?
Yes, thank you. And you get this kink that was first noticed by Nagayama and Otsuki, and it was derived by some previous work that I did in 2020, which is indicating that there might be some CFT responsible for that kink in U2 times U2 theories. You can do the same thing for U3 times U3 theories. Again, there is the O18 model now, given by the blue dot. You get bounds again for all the operators. You don't see any kinks here. So you might believe that, oh, well, there is no CFT then. And so the three flavor massless QCD with effectively restored axial U1 will not be second order. But if you look at the larger region of parameter space, for example, in the RS operator, spin zero operator, you see a very well-defined kink for a larger value of delta phi. And you can then also study this kink and how it behaves as you change n, fixing m equal to 3. And you see it here in the bottom curve, that kink, and you see how as we increase n, it sort of disappears, and the kink that appears is the large n kink of the epsilon expansion that we described before. Now, these kinks are not, specifically the kink in the U3,3 curve here around delta phi equals 0.62 or so. The fact that it exists does not mean that we have a CFT that describes it, but it provides evidence that there might be a CFT with this symmetry that the second order, that the phase transition of QCD might have available in order for it to be second order. So let me summarize that the conformal bootstrap numerically is a widely applicable and robust method for the study of conformal field theories. The bounds that are produced are rigorous and non-perturbative, and kinks that appear in them correspond in many cases to known theories, and it is natural to assume that generally kinks correspond to CFTs that, even though may not be known, may be just as important as the ones that we know from the epsilon expansion and large n. For the case of massless QCD, for both with 2 and 3 massless flavors, I showed you evidence that there may be a universality class available for it to be second order in the case of effectively restored axial U1 at high temperature. Right. Thank you very much for the opportunity.
Thanks, Andy. Questions? Yes.
Can anybody explain to me why a kink should appear where a theory appears? Is there a physical reason?
No. There is a lot of evidence.
I know there's a lot of examples, but is there some
there is
argument that supports it in qualitative
There is no
way?
such argument. Sorry, go ahead.
No argument at all. I mean, I don't know.
Not that I know of. There is no. There is no argument why, for example, in this case, the U2 times U20 kink is so sharp and falls exactly at the position of the analytical computation that you can do. There is no argument.
But I mean, why would it be a kink? Maybe it should go the other direction. I'm trying to understand what kinks mean. No idea. Okay.
Mm-hmm.
Okay, more questions. Denju?
Thanks. I'm wondering, has anyone tried the fixed dimension expansion? You were interested in 3 dimensions, if I understood you correctly.
Mhm.
And there's a complementary to the epsilon expansion. It's closely related, but it's somewhat complementary. Has somebody looked at that in the
Yeah.
fixed dimension expansion?
Yeah, I think these authors here, Calabrese, Paruccini, and some of their collaborators have looked at it in the fixed dimension expansion. Yeah. And Pelisetto, Vicari have done work on the fixed dimension expansion, a lot of work, and I think they have looked at this there.
And it agrees with the epsilon expansion?
Well, it does have, I mentioned it here, it does have this, let me go to the, this is what I wanted to say here in this Pelisetto and Vicari citation. In the fixed dimension expansion that they do, they fix epsilon to 1, then they resum the beta function, and then they look for fixed points. And they have found hints for a distinct universality class, not the one of the epsilon expansion.
I mean, the fixed dimension is, I mean, what?
Sorry, I couldn't hear.
Sorry, the battery is dying in that one. It's the fixed dimension expansion is useful for a crossover. You expect to be able to capture the crossover between those two, so between those 2 fixed points. So that might be an additional reason to look at it. But okay.
Okay, more questions?
Excuse me, may I ask a question?
Yeah, please go ahead.
I'm Takehiro Azuma from Setsuno University, and I want to ask whether the behavior of king is related to the order of the Fed transitions here. I think you showed several plots of.
Yeah, so good. Here, let's use this as an example.
Yes.
We see a very sharp king when n is large enough. And we want to say that this corresponds to the theory U2 times U20 symmetry that we found with the large n results, since there is such good coincidence of the position of those analytical results on this plot with the kink. At some point, as I was explaining back here, there is a critical value of n for which we transition to situation 2, where we lose the fixed point and we have a first order transition at that point. And here you see a reflection of that in the fact that this kink becomes milder and eventually goes away. There is no known at this point criterion for precisely determining this value, this critical value of n, based on the smoothness of the kink or something. This is a work in progress to understand how to, I mean, many people are looking for such a way in the bootstrap to understand how to find the transition from second order to first order transitions. It's not something we can say conclusively. And we don't even know that if a kink exists, that it isn't because of some very weakly first order transition.
Thank you.
So this is a good question, and it's many people in the bootstrap community are thinking about this problem.
All right.
Okay, I see that David Sheikh has a question. Please fire away.
Possibly a silly question if the mic holds up on me. I'm wondering if you can say anything more generally about the importance of these U1 factors. So you spent a lot of time at the start motivating the effective restoration of this U1 axial to motivate looking at these UN. Battery?
Sorry, I couldn't hear.
So I'll switch to a different mic. This one is on. So say the question again. Is it feasible for you to repeat this analysis with SUN groups, and from that be able to say anything about how much the U1 matters more generally?
Yes, very good. That would be the next step we are considering now. Absolutely, yes. it is something, the bootstrap is something we can use for any global symmetry. And SUNF is more complicated than UNF in some sense, because it has more, the group theory is a little more complicated due to the presence of extra invariant tensor antisymmetric stuff. And we want to work it out. We have not yet, but it's definitely something we can do and we're planning to do.
Thanks.
Okay, so let's thank Andy again.
Thank you.